So today I'm going to be talking at Git Merge about Git Merge, hence Git Merge squared. I actually gave a somewhat similar talk 2.5 years ago at Git Merge 2020, where I was talking about optimizations that were a work in progress at the time, and I was discussing what the optimizations were and why I believed in them. I didn't have them all implemented at the time. Since that time, I've got them all implemented. 2 of the 3 that I did have implemented at the time, I've made significant improvements to, and then I found additional optimizations as well. But this time I want to change the talk a little bit because everything is now part of upstream Git and available and in use today. I want to talk with this new merge backend. First of all, what are some of the benefits? Why does it benefit you? Not just in terms of performance, but some of the other features that have come along with that just weren't possible or too difficult with the old merge backend. I also want to, instead of going into as much detail in each of the optimization of how it works, more discuss how I discovered it. What was my journey to get there, at least for the starting path of what was my initial hint to be able to find that thing. And then something that I didn't even know a little bit at the time, some of these optimizations include differences in behavior from the old merge backend, and what are some of those differences. And before I can get into that, I first need to provide a little bit of background. First of all, even though I've said git merge, this actually affects several other subcommands in Git besides just merge, because they all use merges behind the scenes. So things like rebase and cherry pick and stash and so forth. Also, we need to know that in merges, there's a basic idea behind doing a merge, and that's to do a 3-way content merge on each file involved in the repository. The purpose of the 3-way content merge is to reconcile differences when both sides of history have made changes. Perhaps an example would be helpful. So let's say we've got a simple file that exists on both of our branches of interest. I've named the branches side 1 and side 2 because I'm boring. It's easy to refer to them. And let's say that we've got 3 lines in this file of interest on side 1, and we've got 3 very similar lines in the file on side 2, but the middle line is different between the 2. Now, if we merge these branches, what happens to that middle line? It's hard to tell unless you also know what happened in the common point in history, which is referred to as the merge base. So if the merge base happens to match side 1, then we can say, well, side 1 didn't make any changes, so the merge result should be take side 2. Contrast that with if the merge base matches side 2, then we would say, well, side 2 didn't make any changes, so we should take the version from side 1. And of course, there's also the possibility that the version in the merge base didn't match either side, and then we get our standard conflict that we all know well and love. Well, maybe not so much love. Okay, where we get conflict markers, and it provides both versions inside the file, and then we have to go and resolve it and figure out what we want to do. So look for just a second at that conflict, because I'm going to use that as we discuss some of the features. Okay, so one of the new features that came with the new merge backend that we couldn't really do with the old one is a new flag called remerge diff. This comes in handy when you want to look at a previous merge and say, how did this person resolve the conflicts in this merge? And so if you pass the remerge diff flag to either show or log, most of the time you're not going to get any output for a merge commit because most of the time merges are clean. And so it just doesn't show anything. But if there had been a conflict that they had to resolve when they did that merge, then you would see a diff between where they started at and where they ended up to. Okay? So for example, that conflict I had on the previous screen, this particular user in this merge commit went and said, you know what, I obviously don't want the conflict markers, but they also didn't want the line on either side, so they removed them. Those are all in red. They instead added a new line, which was a combination of sorts of the other 2 lines. Another feature that's very similar to this one uses a reference of sorts called auto merge. So if you're in the middle of resolving a conflict, either during a merge or a rebase, cherry pick, whatever, and you've resolved several of the conflicts, but you still have more other ones, and at some point you're like, you know what? I want to know what I've changed so far. What have I changed since the thing stopped and asked me to resolve conflicts. If you run git diff auto merge, you'll be able to see that information. One little note about this feature, it's not actually documented anywhere. Well, actually, it's documented in one place. It's on some slides that was given at a conference called Git Merge 2022, this one. So if someone wants to contribute to the Git community, here's a good first patch, just go document this feature. And if you do that, there will be two benefits. One, I can still be lazy about documentation. And two, we get to grow the Git contributor community. So it's what I call a win-win. The next set of benefits, kind of all connected, they make it easier for us to deal with repository subsets. And this goes in a number of different ways. For example, with partial clones, it provides a massive reduction in the number of files that need to be downloaded on demand by the merge machinery. For the sparse index, this is actually critical. The old merge backend just doesn't work well with the sparse index, and so the new merge backend is basically required if you want to make use of the sparse index. And there's a number of new features that we're working on in the pipeline as well. And so this changes over time. And in fact, between when I wrote these slides and now, GitHub announced earlier this week on their blog that they're making use of the new merge backend on the server side, something that Johannes and I had kind of worked together to make sure we could get that working. So there will be more features coming as time goes on. Another advantage from the new merge backend is I was really focused on correctness issues. There are a number of tests in the Git test suite that are marked as expected failures. People report to us issues. Sometimes they're funny edge or corner cases, or we just haven't gotten to them yet. We still put a test in the test suite even if we don't have it working yet. And about 23 of the tests that I fixed were expected failures that existed before I even started working on the merge machinery. There were another 9 that while I was working on the merge machinery, I discovered additional issues since I was looking at the code really closely, created additional test cases, and those are fixed and worked with the new merge backend, but not the old one. And then also, after the new merge backend became the default, we had a report. I did some investigation. There was an issue with both the old and the new backends, and I only fixed it in the new one. That was another 2 of them. And since our last talk was on submodules, I'll note that 10 of these tests that were fixed were actually submodule related. So it improves things there as well. And on the flip side, there's no tests in our test suite that fail with the new backend and succeed with the old one. So as far as I know so far, it's better. There might still be cases we just haven't hit yet. But as far as we know, the cases we have, it does better on. Perhaps the thing it's most well known for, though, is performance. I spent a lot of time trying to make sure that this new merge backend really succeeded well on performance. I picked a few test cases that were of interest to me, and I'm going to skip, not provide the new timings just yet. As I get to later slides, I'll show those. But if for any given test case, we take the old timing, divide by the new timing, I get some kind of speed up factor. And because I don't want to present 3 speed up factors, I'm going to take an average of those, a geometric mean in this case, and then I'll be able to report a single speed up number. And there's actually several optimizations that I have. I'm not going to be able to talk about all of them today. I'm only going to talk about the ones that are intrinsic to how Git operates or how merges operate. And one little warning, before I get to that, I've got to provide just a little bit more background before I can get into some of these optimizations. First of all, a lot of my optimizations were rename related. So I need to discuss why renames are important. If both sides of history modify the same file, and one of the sides also renames that file, then what's going to happen is that's going to be, the old file will be marked as both modified and deleted, which is a conflict, and then the new file will just be sitting there. And so we'll have 2 files present in the working tree, one that only has changes from the one side, and the other one has changes from the other side. This is a problem because there's no hint to the user that they need to merge these 2 different files. And even if they happen to know that they need to merge those files, it's not obvious how to do so. They're missing the base version to be able to look at. I've seen this dealt with several ways by users. It's usually one of three things, all of which are suboptimal. One, they end up just keeping both files around in the tree, each of which is missing some of the changes from the other. Sometimes they delete one of the two files and keep the other one, still missing changes from the other side. And every once in a while, users do notice that there was a rename. They manually hand apply the parts of the changes they remember, forget the changes that their coworker made to the file on the other side of history, and then include that. But in any case, they often miss things. And this might not be a really big issue if you've only got one or two renames, but if you've got a repository that's dealing with hundreds or tens of thousands of renames, it can really start biting. I also needed to discuss a little bit about how rename detection works at a high level inside of Git. We have to actually do two sets of rename detection, from the merge base to side 1 and from the merge base to side 2. But I'll just look at any given side right now. First thing Git needs to do is it looks at the list of file names in the merge base and the list of files on the given side. If a file appears on both sides, then it wasn't renamed. That gives us a remaining set of files. They might be deletes and adds, but they might actually correspond to a rename. And the way it detects is it says, okay, for every pair of the remaining files, what percentage of lines are found in both? And so it has to fill out this big matrix of similarity percentages. And if you have commits where there's a really long list of files that are unique to the base and a really long list of files unique to the given side, this can be a pretty expensive computation. And for me, this all began a number of years ago. We have a repository that had tens of thousands of renames. You may think that's a lot, but it turns out if you rename a somewhat high-level directory, all files under it appear to be renamed. So you can just rename a few dozen directories and you get huge numbers of renames overall. And at the time, people were writing custom scripts to simulate a cherry pick. They were not using Git cherry pick for a couple of reasons. One, there was silent caps on merge.rename limit. That was one of the first things I went in and fixed. But even if they had a case that weren't affected by the merge.rename limit, then Git cherry pick, with even small patches where someone modified like 5 files and just made small changes to those files, would still take more than 9 minutes long to complete that operation. And a quick warning, I've had to simplify things quite a bit. I don't want to provide all the details. I even oversimplified in a few places, but I'm still providing the true nature of how did I discover these optimizations and what path I went down to get them. So the first optimization is one that I call relevant renames. And it comes back by looking at those custom cherry pick scripts that people were writing and looking at what they did. So they had scripts that would run, create a patch, and then go munge that patch, basically modifying file names in it according to a set of patterns that use repository-specific knowledge and point-in-time knowledge. And then they would run git apply. Seems like a pretty simple strategy. What was the result? Basically, they usually successfully cherry-picked it, and in a matter of seconds. They were cheating and getting away with it. So naturally, my question was, I want to get away with it too. How did they do that? And can I make it more general so that I don't need repository-specific knowledge? So that question ran at me for a while. It's like, Git is trying to detect tens of thousands of renames in the name of correctness, but these other scripts only paid attention to the renames for the 5 files that were being modified and the commit being cherry-picked. Why did that work? And it goes back to some of the things I mentioned on the earlier slides. The purpose of rename detection in merges is to match up files so that we can do 3-way content merges. The purpose of 3-way content merges is to reconcile differences made on both sides of history. What if there weren't changes on both sides, there was only changes on one side? If there's only a change on one side, then we don't need a 3-way content merge. And if we don't need a 3-way content merge, then we don't need that rename to be detected. So that means that we can actually exclude most source files from rename detection. We can reduce the number of rows in that matrix dramatically. This actually isn't too difficult to implement. Took me a little bit of time. It actually goes and breaks the number of tests in the regression test suite because I lied to you about the purpose of rename detection. There's two purposes. But the same basic idea of when do I actually need this source file can actually guide you towards the solution on the other side. It was a little bit hard with the old merge backend because the data structures just weren't applicable. And it took me a while to get it, but this still sends you down the right path. If you implement this optimization, just this one and not all the other ones that I had involved, it sped up those 3 particular test cases I was looking at by a factor of just over 75. Turns out that this also has a behavioral change as well, but it's something that's really well battle tested in Git itself. In particular, this behavioral change is that if there's multiple valid rename pairings, meaning you have multiple files that are very similar in each commit, then excluding some of those source files can cause the other files to be paired differently than they otherwise would have been. The reason why this is battle tested is because Git am-3, it has a function called build fake ancestor, but it's algorithmically identical to what you would get with a naive form of this optimization, the one that breaks directory rename detection, applied just on the upstream side. The upstream side is the one that usually has most all of the renames. So anyone who's been using Git am-3 has actually already been using this optimization. And even if you don't directly use it, a lot of other people do directly use it, and you've probably indirectly used it because it powers one of our backends in Rebase. Just like Merge, Rebase has multiple backends to it, but it's a little bit different in that you usually don't explicitly call out the backend. Rather, some of the features of Rebase are supported in one backend, and some of the features are supported in a different backend. And so which backend you get is dependent on which other flags you provide. One of the backends is based on cherry pick, one's on Git am-3, and we actually changed what the default was if you didn't need any of those specific behaviors a couple of years ago. And so this optimization actually changes the cherry pick backend to match what Git am does. So we've made things more consistent, actually, in Git, which is a nice benefit for this as well. And actually, we did a lot of work a few years ago to try to document all the differences between the Rebase backends as a starting point for let's try to remove some of these differences. This was one that we missed. I just didn't know about it actually until like a few months ago as I was going over this in a little bit more careful detail. The second optimization is a lot easier to discuss. I call it no copy detection. And the idea here goes back to the fact that Git stores hashes not just of commits, but of individual files and trees. That provided a really simple optimization idea, one that was implemented, I think, before I ever even got involved in Git. If 2 files have the same hash, treat them as an exact rename and remove them from the similarity percentage matrix. It's a really simple idea, but the implementation didn't actually do that. It would go and find the exact renames and then only remove the destination file. So basically, it would reduce the number of columns, but not the number of rows. And the reason for that was the code that did rename detection was also responsible for copy detection, and it wasn't fully aware there was a missing place in one location of where it was knowing whether it was trying to do both or only trying to do one. Merging doesn't have any use for copy detection and turns it off, and that basically meant that what the code was doing was wasting time looking for a better than an identical copy, which it wasn't going to find. If you implement this optimization, turn off the other one that I did, so only this optimization is active, it speeds things up by a factor of over 2, and there was no behavioral change from this one. The next optimization I refer to as caching renames. Really simple idea, less simple implementation. But at one point, I was rebasing a long sequence of commits, and I noticed a little pattern in the output. And namely, the pattern was the exact same line, every line in a row. And in particular, even the number in parentheses. The numbers in parentheses represented how much work had been done towards rename detection. And despite being a very large number, it was identical every single time. And what that meant was, if you go into the algorithm, Git, when it needs to rebase a sequence of commits, it takes the first one, says I need to do some kind of merge operation with that, and that says, great, I need to know what renames were done on the upstream side. Git goes off for a few minutes, comes back and says, there's 26,000 renames, here they are. Then it finishes with the merge with that commit, gets it all done, goes to the second commit and says, I want to play that on top of what I just did. And it says, great, I need to find out if there are any renames upstream. Goes and looks, computes for a few minutes and comes back, hey, yeah, there's 26,000 renames, the same 26,000 we computed before. And then it repeats this for every commit that's being rebased in the sequence. And so naturally the question comes up, why don't we just cache it after the very first one? Really simple idea. A little bit more complex to implement, as it turns out. But when we go and implement this idea, if I turn off the other optimizations, then this optimization by itself speeds things up by a factor of just over 5. There is a behavioral change with this one, and I can't go into details on it because it's just too complex, but it's a very tiny corner case. And I'll also assert that it's no worse. If you want to check me on that, there is a file in the Git source tree called documentation technical remembering renames.txt, 700 lines of dense text, which is basically a proof to try to show that this optimization actually is safe. There's all kinds of funny cases associated with it in trying to prove it, and it turns out we did find while I was doing that there is this one case where things are a little bit different. But it goes over everything in detail around that and shows that and argues that it's actually an improvement. It's always better and what the user would expect. Occasionally, people come with ideas of more comprehensive caching of renames of some sort to try to speed up rename detection. I'm a little bit skeptical of some of those, especially when you start storing that cache on disk. I think there's various ways to make it unsafe, and there's actually a lot of ways to make it less performant, surprisingly. But this optimization helps out. The next optimization is what I refer to as base name guided rename detection. So here, I actually went and looked at matrix sizes. So at the very start, if I didn't have any optimizations turned on, not even the really old exact rename detection, I would have had a matrix size that was tens of thousands of rows and columns each. After I do exact rename detection, it drops me down to order of thousands. And then after I do relevant renames optimization, it drops me down to a single row, which means that I really only need to find one rename left. And that may sound like I've removed most of the computation, and I have done most, but the performance timings aren't quite as good as these numbers would lead you to believe, because it turns out that there's a really expensive setup step that has to be done for each file in the sources, so for each file in the rows and each file in the columns. And so it turns out whether that number of rows is 1 or 20 or 30, it doesn't matter a whole lot. The number actually has to be fairly big before the matrix computation costs more than that initial setup does. So I really, really wanted to avoid that big, expensive setup cost. But in order to do that, I somehow need to get this one other stinking case out of the way. So the question comes up, can I somehow identify likely rename pairs without doing that full matrix of similarities? I'll start by first changing the file names a little bit to match my case a little bit better. And then basically have to look at it as saying, I don't have that matrix of similarity percentages. I don't know anything about these file contents. Can I somehow still guess what is a likely rename? And after I solved this, I gave this to my daughter, who was 5 years old at the time. And it turns out she was able to solve it too when I gave her a tiny hint. Okay? And this really mattered in my case because I'm like, I know I can see in my file list that I have a file with the same base name on both sides. Why do I have to compare this one file to 5,200 files when without even opening the file in the editor, I'm pretty sure that that's the one that's the rename? And that may sound like cheating, and I was worried that I was cheating. So I went and gathered a bunch of statistics. I went and looked at existing repositories and said, how often is it that historical renames in these existing repositories just moved a file into a different directory without changing the base name. And I expected it to happen some of the time, but I was surprised just how frequent it was. And it also seemed to me that the bigger repositories tended to do this even more often. And the bigger repositories are also ones where the rename detection is going to be even more expensive. So that gave me the simple idea. Let's go for it. Let's check if files with the same base name are similar. So I know they have the same base name. I'm just going to compare those ones first. If they have a high enough similarity where I'll require a higher threshold than I normally do, then I'll count them as renames without comparing them to everything else in the matrix. If you implement this optimization and turn off all the other optimizations that I had, it speeds things up by a factor of over 5. It does have a behavioral change, probably fairly obvious on this one because of the way it's described. If you have a file that could have matched a file with a different base name, and that would have been a better match, you won't see it because you first matched it up with a file that happened to have the same base name that it was similar enough to. We've documented that difference. We also provided an ability for people to be able to test this out and control how much additional similarity is required with an environment variable called get base name factor. We didn't think to document it though, so another opportunity for you to get involved. But one benefit that came with this actually that might give you a little bit more comfort with this change is that we didn't implement it in the merge layer. We implemented it in the diff layer. And what that means is it doesn't just affect the new merge algorithm, it affects the old merge algorithm, and it affects any diff that you compute. Which means that you've already been using it in all Git releases since Git 231, so for the last year and a half. And we haven't heard anyone scream so far, so maybe it's fine. The last optimization I want to look at, I call trivial directory resolution. This one is the one that isn't rename related, although it needs some ideas from the other ones. So again, I have to go back to the fact that Git doesn't just track hashes of commits and of files, but also of subtrees. And so you can think of the merge operation as first taking the top level trees for each of the 3 commits, recursively walking into those trees to gather all the files, matching up files for 3-way merges based on renames that you've detected, doing 3-way content merges of those matched files, and then using those resulting results to write new subtrees in a new top-level tree. But a question that may come up after you look at this enough is, what if one of the subtrees matches between the merge base and one of the sides? Can we just avoid recursing into it and say, you know what, I want the tree from the other side? Because if the top-level tree, or if some tree matches the merge base on the other side, then every file underneath it is going to match by construction. It's a simple idea. It would be really nice, but unfortunately it breaks rename detection. Not just directory rename detection, but regular rename detection pretty badly. And in fact, I had thought about this before my talk 2.5 years ago, but I thought it just wouldn't work. It would break things. But I discovered since then how to get it to work, and there were a few keys to unlocking it. First of all, if you could somehow know before you started that there weren't any renames, then this optimization is safe to do. And now if you start combining that and think a little bit further and combine it with some of my earlier optimizations, you can dig in a little bit further and say, you know what, if there aren't any relevant, before I get into that, the problem with the first one, if there are no renames, then the optimization is safe. There's no way to know if there are renames without recursing into those trees. So it doesn't actually help you. But if you go a little bit further, you can find out if there are no relevant renames, then you can do the optimization. And that one's a lot more helpful because you can find out if there are any relevant renames without recursing into those trees. So the basic trick is you defer recurring into those trees until you find out if there's a relevant rename anywhere in your entire tree. If there are any relevant renames anywhere, then you have to recurse into all of those trees. But if there aren't any, then you can avoid recursing into all of them. If you implement this optimization, turn off all the other ones, then you get a speed up factor of 4.6, at least for my test cases. And it doesn't provide any behavioral changes. But of course, one thing is I've kind of relied on the idea of relevant renames here, just in order to be able to implement this optimization. So now if we combine all of these, I can put them together, and I get a whole bunch of optimizations and some speedups from those. But the overall speedup is not the product of these speedups. You notice several times I mentioned if you turn off all the other optimizations and run just this one. Because it turns out there's a lot of cases where multiple optimizations could apply, and you can only pick the best one, and then the other ones cannot be applied. But one nice thing about that is a lot of these have special cases where they apply. So that means that even if one of them doesn't help you, another one might be able to. And this is very much a case of your results will vary. My test cases, 2 of them had a huge number of renames, tens of thousands, because that was mimicking what was happening inside one of the repositories of interest. You probably have cases with far fewer renames, in which case the first 4 optimizations won't benefit you quite as much. You might also have much smaller repositories. These optimizations all tend to benefit more with bigger repositories. But one thing that's particularly interesting is that the trivial directory resolution helps more when there are fewer renames. So for example, on my few renames test case, that trivial directory resolution gave a speedup factor of 70. Some of these optimizations, they also depend a little bit on cases like the caching renames only helps out for rebases and cherry picks where you're doing more than one commit. And there's 2 optimizations, the no copy detection and the base name guided detection, that actually help for things other than merges like diffs. One other thing I'll note here is that some people are testing out the new merge backend. Like for example, when Stoli had mentioned numbers with mono repositories, he compared cases where there hadn't been any rename detection involved, which meant that he was only testing the final optimization. So you get very different numbers depending on what your use case is and what you're comparing to. But in my test cases that I was looking at, I'll now show what the new timing numbers I got. And importantly, I was really wondering if I could get all of these less than a second, and worked really hard until I could either discover, is it possible, or why can't I do it? And you'll see that even in my test cases, the speedup factors varied quite dramatically. If you're curious for more details about the optimizations involved here and some that I didn't even cover, I've got actually a 6-part blog series that you can go read up to learn more about it. If you just Google for optimizing Git's merge machinery, and especially if you can find part 6 because it has backlinks to all the previous ones, then you can learn more of these details. Thanks for the time.